kind of is a very important table to how to change things. So there'll be problems that says negate using conditional, negate using converse conditional, you using biconditional, right? So then it has a column for symbols and then what type of sentences. We've already been doing conditional. Conditional is the if then statement. If P, then Q. Converse just means you swap statements. So Q comes before P. And again, we talked about this last week where we kind of followed the alphabet, P's first, Q's second, when we relate to each other. So that's the biggest difference between conditional and converse conditional. The statements just swap places, but it is an if-then statement. Inverse conditional is when you bring in our little not. So if not P, then not Q. And then contrapositive of the conditional is basically back to the converse one. If not Q, then not P. And biconditional kind of means goes both ways, if and only if. So P leads to Q, but Q also leads back to P. So this little table is kind of the words and the symbols. So they will have you rewrite statements based on what type of negation or non-negation basically off this table. And so one of the first key definitions here is a logical equivalent statement. So these are statements that have the exact same truth values in all situations. And so it kind of looks like an equal sign, but with 3 lines. So my graph is not drawn perfectly, but they're supposed to all be the same length. But it is a 3-linked equal sign. You can kind of see it in De Morgan's law. And so an equivalent statement is if I build a truth table of the left and I build a truth table of the right, the 2 truth tables would be identical. And if they are identical, that is what we call logically equivalent. All right. And it's important because in 3.4, we're going to learn something that is tautology. Tautology means that your truth table finishes in all T's, all truths. That is the difference between logically equivalent and a tautology. Logically equivalent just means the tables are the same. Tautology means that your entire truth table finishes in all truths. If it has one F, one false, then it is not tautology. But I can have false statements in a logically equivalent statement, right? So that's the big difference between those definitions. So remember, De Morgan's law is basically a way to move the not around. So here, and when we do that, it usually ends up flipping our statements. So in our first one, this is not P and Q is logically equivalent to not P or not Q, and vice versa. And we proved this back in chapter 2 of the Venn diagrams. So not P or Q in parentheses is equivalent to not P and not Q. So you can kind of see it gets rid of the parentheses kind of thing. And you don't always have to have truth tables, right? So I can do it with statements. So I have a statement here, for example, it is not true that I missed class on Tuesday and forgot to email my instructor. So if I use De Morgan's law and do its logical equivalent, then I do not miss class on Tuesday, or I do not forget to email my instructor, right? So if I write this out, so we can kind of see it, this is P, this is Q, right? I have my or statement, and then I put this in parentheses, and the not's on the outside, right? Now I'm down to myself. Or is that symbol correct? I want to remember. This is why, again, I use notes. I always get them backwards. Not. Yeah, no, I'm right. Good. Phew. Phew. That is the and symbol. I'm okay. And then if I use De Morgan's law, I did not miss class on Tuesday. So there's my not P. I have my or, and I did not forget to email my instructor. So there is my not Q. Right.
I remember and because it's like an A, the capital.
Thank you. Yeah, there's a few things in math that get me because I've memorized them poorly. and then I can't unmemorize them. So this is one I keep getting my ands and ors, so I'm gonna try to remember that. And then when I do college algebra, my cosecant and secant, my inverses of my tangents and cotangents and sines and cosines. Sometimes, and you might not know what I'm talking about, you haven't taken algebra yet, but I always get secant backwards. I just convince myself it is the inverse of sine, but it's actually the inverse of cosine. And I just keep messing it up. Which is one of those things when you memorize them wrong, it takes a little bit to unmemorize them wrong. So another logically equivalent kind of De Morgan's kind of situation is I can also do things with if then. So P, if P then Q, so not outside, and I distribute the not through, it becomes a P and not Q. So there's lots of these rules. That's why I write them down and you can refer back to them. And we can always negate these things. So here's, if I go to Miami Beach for spring break, then I will have a good time, right? And if I negate this using the conditional, I go to Miami Beach for spring break and I do not have a good time. So again, here's my if, and then my then. This is my P. Here is my friend the Q. I go to Miami Beach and I do not have a good time. Right? And so if we want to prove this using a truth table, right? Because that's what it says, right? Something to be logically equivalent is I should finish with my good old truth table. So that looks like it's actually going to work this time. Yay. So let's build one again. So remember, first we know we have two statements. So I give it a P and a Q. And then I do my pattern, true, true, false, false. And then I alternate true, false, true, false. And again, I know I have all my statements because I have two statements. I square it. And I should have 4 rows, which is exactly how many rows I have. And they're not repeating. So everything is good to go. So now we go back to our truth table. Oops, I don't want to be in draw. I can type this that way so I can come back and look at this later if they want. Escape. Right? So if then Q, remember that is the broken promise statement, right? So the only time I get a false on my broken promise statement is when P is true and I don't hold up my promise. So I go true to false, right? So true to true is okay. And again, if you forget these, look back on 3.1 and make sure you have those in your notes, but that's where they're at. So true to true is okay. True to false, there's my broken promise. So that is false. False then true is okay. False and false with if then statements is also okay, right? And now we're trying to prove this first piece of our logically equivalent statement. So not on the outside of the parentheses literally just means I change from false to true, and that to to false to false, right? Because that's all the not says. So in parentheses, then once you have it in parentheses and you've solved what's in parentheses, I can then just apply what's outside. So that's how that side finishes. Then we're going to finish the other side. So we need not Q. So I'm going to take all my Q's and change them. So it goes from true to false, false to true, true to false, false to true. And now P and not Q. So remember, and is only true when everything is true. So if one of them is false, the entire thing is false, right? So again, I'm comparing P. So again, if you put your fingers on here, I'm comparing this first column, P, and then this last column, Q. So I have I'm getting rid of draw so I don't mess it up. I have a true, then a false. So this guy is false. I have a true and a true. So this guy is true. I have a false and a false. So this guy is false. I have a false and a true. So this guy is false. And if we compare the two highlighted columns here, oops. Well, let me highlight here. Why? Oh, it's the wrong thing. If I compare these two highlighted columns, you can see they finished in the exact same order. So these statements, by definition, are logically equivalent. Questions on logically equivalent?
No, but I have a quick question and it's a dumb one, but I don't care. All
Never
right,
a dumb one.
explain, I know, but kind of. So when parentheses are around something, what is that actually saying?
It's saying, just like it does in math, do what's inside first.
Okay,
Just like order of operations. Yep. So
Okay.
since that's saying
That's-
P and if P then Q, that's why I created that column first, because
Yeah.
just like the rules of math don't change here. I do what's in parentheses first, and then I do what's outside. That's a great question. All right, so here are some examples of using that table above. So find the inverse of if P then Q, right? And I already have the answers here, so I guess I could just one highlighter. Draw. I could just delete them, but we can just talk about them. Right, so find the inverse of P and Q. So we come back up here to our table. The inverse just means they both become negative. So I come back down here, they both become negative. Converse means they just swap places. So my P went from last statement to first statement, Q from first to last. Contrapositive, again, they swap places, but they also swap signs. And inverse, again, they just swap signs. So just following how these rules, so when you go to do some problems and it says find the inverse of the statement, then you just are basically falling right out of this table. And then we did a couple examples when you can put them in words. All right. So how are we? So we're feeling okay about truth tables? Getting there? All right, so I want to do this then for a minute. I want you to grab a piece of paper and I'll give you about 5 minutes because I'm actually going to step away for a minute. So I want you to create a truth table. So create 2 truth tables. Create a truth table for this first piece and then create a truth table for this piece and see if these things are logically equivalent, right? So it says it can go both ways. So basically I'm asking you, if you create a table for the left side, is it logically equivalent to the same on the right? All right, so I'll get everybody to, it's 2:55 on my clock. So at 3 o'clock, I will come and start building this with you and then we can compare answers. And I'm going to pause the recording so you can go back and watch. You don't have a 5-minute gap of just silence. So I am pausing. So if you all want to talk to each other, you may. You're not being recorded. Okay. How we feel like we did?
It's a lot harder when you're not doing it.
Yes, it can be. Oh. You can see, if you scroll over a little bit on the notes, if you actually add them up, you can see I already have the answer. But we'll still do it again. I'm just going to delete everything. When you go out of draw mode, you always have to hit escape. That's why I always end up having a dot everywhere because I forget to hit the escape button. All right, let's draw. Where's escape? All right, so this is how I built my columns. You might have built them a little different, and that's fine. As long as we end up in the same results, then everything is good. Right, so I would start with not P, because I'm just doing these one at a time. So P goes from true to false. And then I'm just gonna turn my cap on, that'll make it a little bit easier. And then true to false, and then false to true, false to true. And then we have our good friend OR. And so remember, OR is always true unless both are false. So I'm comparing columns 2 and 3 now. So true and false gives me a true. False and false gives me a false. Two trues is a true, and a false and a true is a true. Now I'm going to compare my first column P and my fourth column I just created, and it's an and, so they are only true when both are true. So true and a true gives me a true. True and a false gives me a false. False and a true gives me a false. And then a false and a true gives me a false. So we should have finished with a 1 true and 3 falses. We do okay? Any questions? All right, so I'm assuming everybody that played along got the same answer I did, since no one's got questions. And what are we comparing here? So if I scroll back over, we want to prove that that's the same as P and Q. So this first one is done. So I will go to draw for a minute, right? So this is the left side. And now we're going to see if these things are logically equivalent, that the left is the same as the right. So P and Q compares the first 2 columns. And again, they're only true if both are true, right? So I have a true and a false. So that's a false, hit the wrong key. False and a true is a false, and 2 falses is a false. And you can see these things are logically equivalent because I finished with 1 true and 3 false. Now, if I take this one step further and I do if and only if are true if both sides are the same. So true and true gives me a true. False and false gives me a true. False and false gives me a true. False and false is true because both sides are the same. And so this is what we call tautology. I think it's A-L-O-G-Y. Because everything finished with all trues. So that is a tautology statement. So logically equivalent, same results in the end. Tautology is a column of all trues. Questions on this section? Okay.
Yeah, I didn't get what you got. Can we
Okay.
go over that one more time, just a little slower? Like you can leave the answers in there, but just one
Yep.
more time.
So we'll walk through the steps. So we start with creating our columns for our statements, right? So we have P and Q because we have 2 statements. And so the pattern I always do is 2 true and 2 false.
Can I ask why? I mean, will it come out the same if you don't do it that way?
The key is just making sure that you have 4 rows with every row having a different scenario.
Every combination of true and false that you can have.
Yes.
Okay.
So
Okay.
you may have them in a different order. So if you might have finished with false, true, false, false. That is also true as
Okay.
long as it lines up. So it's more, don't worry that your table looks exactly like mine, but do we have the same values for the same row? So my first row may be your third row, and that's okay. There's nothing wrong with that. It really just, but are we the same going across? And if we're same going across, then we have the same answer, even if it doesn't look the same. Right? So I always start with this pattern because it just helps me make sure I don't miss any situations. Okay. If you wanted to start alternating the first and then pairing up the second, that is completely fine as well. The key is just making sure that you have every possible scenario covered. And because anytime you have 2 statements, you're going to have 4 rows. You have 3 statements, you're going to have 8 rows. You have 4 statements, you're going to have 16 rows. So you can see every time you add a statement, your table grows exponentially.
Okay.
Right? And then just making sure you have the pattern. So this pattern helps when you have bigger rows, more rows than the 4 ones, not so bad. So we get that first, make sure we have every situation. So this is step 1. Make sure you have every situation covered. Then step 2, create enough columns that you can solve the truth table. Now, Could I have just created one big truth table for this statement? The answer is yes, you could have. Now, would I recommend it? Probably not, because that's a lot of different conditional statements that you're bouncing between to make sure that you don't mess it up. So I break mine down by each part of the statement. Again, not required, but it's one of the, it's kind of like doing order of operations by hand. If I do one operation at a time, then it helps me not miss a step. Can I do all operations at the exact, in one step? Of course you can, right? So this is the same thing. But the step 2 is creating columns to get to your answer. So these 2 are optional. I'll call them OP, right? Not required. They're optional. This third one is required because that's the answer you're trying to get to. So I created 2 optional columns to help me prove that this statement. So I did a not P, and then that means I just take all my values from P and I inverse them. So my trues become false, my falses become trues. Now, when I go to do my next optional column, I am going to take this column and I'm going to compare it to, this column, P versus Q, and it's an OR statement. And so the only time, I made a mistake and no one even caught it. No, I didn't. Okay, I thought I did make a mistake. I'm okay. I was thinking it was and all of a sudden. So, or, I'm comparing these 2 columns, and or only is false if both are false. If one of them is true, then the whole thing is true. So comparing, I have a true for a Q, so I don't even really care about the not P, but I'll check it anyway as a false. So that is a true. The next one, they're both falses, so that is a false. And then both trues is a true. The last row, one is a true, so the thing is a true. Then I get to my required column, and now I am comparing P, so this column, with the column I just created. So I'm comparing the 2, and this one is an and statement. And is only true if both are true. So it's kind of opposite of the or. Or is always true unless both false, and is only true if both are true. So now I'm comparing the first and the fourth. So I have a true and a true. So they're both true. So that's true. P is true. My stuff in parentheses is false. So therefore it is a false. P is false. Well, I don't really even care about the next one, but I'll check it anyway. Is a true. It is a false. And then false true is then again a false. And so I have finished doing the left side. I have created a truth table showing the final. Now remember, what is a truth table? A truth table is just all possible situations. It doesn't tell you which situation you are in. I just have a table that I can refer to for any written situation I find myself in. All right. So basically, if I have 2 statements, right, and this will show how tough this can be. Let me see. Do we have an example of statements on this table? Where has everything been? Yeah, so we can do the Miami Beach problem, right? So if I go to Miami Beach for spring break, then I have a good time. So my first statement, I'll try to type it right here. Oh, I'm in draw mode again. So P is the statement. I go to, I'm in caps locks. I go to Miami Beach for spring break. Come on, work with me. That's supposed to be a small p, but my OneNote always auto capitalizes. And then Q, I knew you were going to do that to me, is I will have a good time. So if I write this out in words, what I'm trying to show here, if I want P, I'll do the easy one first. P, I'm not going to go in math mode, so I'm going to use this little caret key on my thing. If I want to write P and Q as a statement, I really gotta figure out how to shut this auto cap off. Then this is, I go to Miami Beach for spring break and I have a good time. The next one is not going to sound very grammatically correct, but we will try to write this out. And then now I'm looking for my humanities degrees to correct my grammar. So I am doing P. So I'll write it out real quick. P and parentheses, not P or Q. If I write this in verbiage, let's see. I go to Miami Beach for spring break and I think I'll write this. Guess, and I do not go to Miami Beach. Or I have a good time. I don't think I have this typed out grammatically correct. I'm trying to think of how to grammatically add the parentheses in. If anyone has any ideas, I am all open. I go to
Wouldn't you
my-
have to do the parentheses first? So
Yeah,
it really
what-
be,
Go ahead.
so wouldn't it really start with, I don't go to Miami Beach for spring break and I have a good time?
But then where does the or come in?
Or instead of and, sorry. So I
Yep.
don't go to Miami Beach or I have a good time.
Command X. So. So I do not go to Miami Beach for spring break, or I have a good time and I go to Miami Beach. All right, that goes a little bit smoother than what I had. They're always tough to write in words, so that's why on the test I always use drop downs, because then I limit your choices. It does help. Versus like last class, I think we were talking about all the different ways to write it, and there was multiple right answers. Yes, for the test there'll be drop down boxes, so I limit the things you can pick, so it makes it a little easier on both of us. But there you go. So this is kind of what we're trying to prove, that these two statements are equivalent using truth tables. And then, so what the truth table does is telling me, did I go to Miami Beach or did I not? So the first thing is, my scenario is I did go to Miami Beach and I did have a good time. The second one is I did go to Miami Beach, but I did not have a good time. First one is I went to Miami. I did not go to Miami Beach, but I still had a good time, whatever I guess I did. And the fourth thing is I didn't go to Miami Beach and I did not have a good time. So I don't know what has happened, right? Because I haven't gone to Miami Beach yet, technically, but I have a truth table showing me all the possible situations that can happen. I can go and have a good time. I can go and not have a good time. I can not go and still have a good time, or I can not go and just stay in my dorm room and not have a good time. Right. So that's think of the truth table of that. It's not giving you the answer of what's going to happen in the statements. It's saying here is all the possible situations in the statements. And then you can just say, all right, what are my choices kind of here? That kind of help clear up what the purpose of truth tables, not so much how to construct them, but the purpose of them.
It does for me. I think I just have a trouble figuring out what my top line is supposed to be, like P, Q, not P.
Those are just really
parentheses.
just letters. So it doesn't matter. It's a small lowercase letter out of the 26 that are in the alphabet. They really don't matter. AB, JK, you know, we've kind of put them together as kind of the pattern, but it doesn't always have to be. I mean, I guess there's nothing saying you can't do A and Z. And that's why what I haven't done every single time before I do a truth table, actually I didn't even do it up here. What I got to get in the better habit of is, which takes us right to the next lesson, is labeling these things. So you can see in arguments, which is not much math, a lot of definitions, you should always label your statements. And that way, when you go to build your truth table, you know what statement you're referring to. So I didn't do very good with it here. I think I did better with it here. You should always label your statements with a lowercase letter. No, I didn't do good here with the 49ers win thing, but I did it with the spring semester one. So if you label them, that helps you kind of understand what go in what label. So you can see here I used A and B. I think down here, down here I'd even use A, B. I used C, D, and E because I used A and B above. And then
Oh,
back
no,
here, we
that's
went,
not quite what I meant. What I meant is like how to figure out how many different scenarios I need on top. So not
oh,
quite the letters, just how do I figure out that I need 6 boxes and I need P, Q, not P, Q, and like that.
so what I would kind of do is for those is look at what's being asked of you. So when I first look at this, I can see I have a not. If I have a not, I always add a column just for that not. And then I have a thing in parentheses, so that should have a column all by itself. And then I need to have a column for the entire compound statement. So that's how I know where I end. Then how many steps in between is really just to your comfort zone of, do I want to do each of the statements independently or individually, I should say, or am I comfortable enough to kind of combine them? So there is no right or wrong. Well, there is a wrong answer, but there's not one answer here. So you could build this. You could solve this with one column, or you can solve it like I did with 3, right? Or you could solve it with 2. It's really a preference for how many extra steps you want to do. So to give you something to relate to, say we're solving this. So 2 plus 4 parentheses 5 minus 3 divided by 2, right? Could I solve this equation all at once? Yes, well, not equation, expression. I could. Or I could do it in pieces. I could do 5 minus 3, which is 2. Then I can multiply it by 4, then divide by 2. So that's what you're doing here as well. You're asking yourself, where is your comfort zone? Am I comfortable doing more than one step at a time? Then you're going to have less columns. If you want to only worry about one thing at a time, then create them all. And I guess the better answer to your question, now that I'm speaking out loud and I'm thinking about it, if I go to here to my truth table, think of every one of these bolded statements as a column. I may have a column for the and, a column for the or, a column for the if then, and what I'm missing here, because it's on the other table, I would have a column for the not. So every time you see one of our symbols, here we go, and that's what I can do. This is better. Oh, why'd you go? There you go. Every time I see one of my logic symbols, each symbol will get its own column. That's how I do it. Because that way I can focus on one symbol at a time instead of trying to do multiple symbols at once.
That is perfect. Thank you.
Yeah. Yeah, so I guess that's it. I create a column. That's the simplest answer. Create a column for each of the symbols. And then you must have a column when you bring all the symbols back together, basically what you're trying to prove. Good question. All right. Lots of chat. Good, good. I love that you guys are talking to each other. So 3.4 is should be very clear in logic, since our class is logic. But it really comes down again to what are facts, and just watch the news for 5 minutes and you can understand why this lesson's becoming harder and harder for me to teach. Because before, when we used to believe what was facts, is very different nowadays. But that's kind of what logic is built on. So maybe all of us need to retake this class, including some of our politicians. Because that's arguments. And what makes something a valid argument is it valid in the end? And if it's not, then it is an invalid argument. Or what we call a fallacy. So 3.4, lots of definitions again. So I've typed out almost all of them here for you. Still read the book because they give you a little more examples than I do, and maybe a little clearer. I kind of paraphrase some of these, but we'll go through these. So an argument is just something that consists of a series of logical statements. So this is very similar to the completing project 3. Project for chapter 3 under the instructor version, where I said create a logic argument of logic statements based on social media, right? Or you can do, I think Zach was the one that did the one with the light bulb, which they write it all out for you, versus the one I picked is you're going to kind of build your own kind of thing, right? But that's what it is. You're going to build an argument, and all an argument is it consists of a series of logical statements. So going back to 3.1, we talk about what is a logical statement, right? So a premise is the beginning statement, right? And so in the videos I just created on YouTube, per request of you all, I do a couple of the homework problems, and in there I kind of talk about a premise. And basically, when you're solving the homework problems, sometimes the premise is hard to see, but the conclusion's easier to find, right? So the premise is the beginning of the statement. The conclusion is the end. So sometimes if you can't really decipher what the premise is, look for what the conclusion is, and you can, if that's the conclusion, therefore the other thing has to be the premise. And a sound argument is a valid argument using true premises. In other words, when I create my truth table, does it follow the truth table? And if what I have written in words follows the truth table, then it is a sound argument. Kind of what I was trying to show back there with the Miami Beach one. And so inductive reasoning and deductive reasoning goes back to chapter 1, right? So inductive reasoning is a line of arguments that takes specific examples as its premises, then draws a general conclusion, not a fact. It draws a general conclusion. Deductive reason is something that we commonly accept as real facts and make a case of a certain conclusion. Just like we were talking about today, I had an example back in chapter 1 about this, where we only have snow days on Tuesday. Here it is again, a Tuesday, and we have a snow day, right? So just because it happened again doesn't make it a fact, right? So it is still inductive reasoning, even though somehow we keep having snow days on Tuesday. It is an inductive reasoning. We're drawing a conclusion based on specific examples. Our specific examples are past snow days at CM, seem to always fall on Tuesdays. And we have another snow day on a Tuesday. Deductive reasoning is if by fact it only snowed in this state on Tuesdays, then maybe we could argue deductive reasoning, but we all know that's not the case. So we're using inductive reasoning about snow days here versus deductive reasoning using things that are considered facts. A valid argument is a deductive argument where the conclusion is guaranteed from the premise. A valid argument does not guarantee truth. All a valid argument is there is a link between these things that connect the premise and the conclusion. And if it is a valid link, then it is a valid argument. All right. An invalid argument is an argument where the conclusion is not always guaranteed from the premise, right? And then fallacy is an error in reasoning that leads to an invalid argument, which is probably what happens more in society than anything. So consider whether the following is a valid argument. So all dogs bark. I have a dog, therefore my dog barks. Is that a valid argument? Can I get from A to C?
It's tough to say, would you consider dogs that don't have vocal cords? Because they can bark.
That's
Is
true.
that
Right, so I guess we should add in here, you know, some that maybe don't have a medical condition. So yes, there's always those, but we'll try to keep it. So I forgot I have a class full of nurses. So I gotta be careful with my statements here now. We'll go on the assumption that the dog has no medical issues. So since we know dogs do bark, and then I have a dog and I can easily turn off my camera because she's actually sleeping right behind me. So therefore my dog barks, right? So that's where again it becomes a little tricky. So and we're in society and logic that makes it hard. There is things that happen that we have to take into consideration sometimes. But play the non-medical role, I would argue that this is a valid argument. There will not be I will not have anything on the test. Well, what about this? They're going to have a clear break in them, right? And so a good example where there's a break is example 2. So birds use their wings to fly. Chickens are birds, so therefore chickens can fly. Now this one again, I guess you could argue, you know, if you have chickens, technically they don't fly, but they can get their wings flapping enough. They can stay off the ground for a few minutes, but they're definitely not going to fly in the sky and fly away, right? So this one is a fallacy because we know that chickens can't fly. So just because the first 2 are true statements, right? Because birds use their wings to fly. And again, I'm not a biologist, so I know someone might say that technically they don't. I am not trying to get into that deep into it. And chickens are birds. So there's an issue with this argument because we know technically chickens cannot fly. And then on my third example is I voted in the last election. So to vote in the US election, you must be a US citizen. Therefore, I am a US citizen. Right. And so the law says that you have to be a US citizen to vote in the election. And therefore, since I voted, then I must be a US citizen. And so, like it said, to prove something is a sound argument, our truth table must be able to be completed, right? So I create my small truth table. Statement A, statement B, and then I'm a US, therefore I'm a US citizen, so an if-then statement. So A is true, so I voted in the last election. All right, I am to vote in an election, you must be a US citizen, right? So that is true. Therefore, I'm a US citizen. So if both A and B are true, then C is true, so that's good. So then we go with the second option. So I voted in the last election, true. I am not a US citizen, false. So hopefully someone caught the vote where I'm lying and I actually didn't vote in the last election because therefore I'm not a US citizen. So there's where I've kind of broken the promise. So that follows the truth table. I did not vote in the last election, but I could still be a US citizen, right? So therefore that row is also valid. And then finally, I did not vote in the last election. I am not a US citizen. So therefore I'm not a US citizen. So that is also a true statement. So my truth table supports my 3 statements. So I have a valid sound argument because my truth table supported my findings. Questions?